Hello, welcome to another chemistry video. Today we're going to talk about different chemical names and formulas. There are many different systems for naming chemicals when given their formula. We're just going to talk about a few. If you're given the formula, you should be able to produce the name, and by the same token, if you're given the name, you should be able to produce the formula after watching this video, and that goes for either ionic or molecular compounds. Okay, before we start, let's talk a little bit about subscripts and what sort of peculiarities you're going to run into in a chemical formula. A subscript is the little number right here. See this little number that's down low after the C for carbon, you've got a 2. That's called a subscript. And what it tells you is how many atoms of that particular element there are in a compound. So in this particular formula right here, we have 2 carbons and we have 8 hydrogens. Okay, if we move over here, water, H2O, we have 2 hydrogens for every 1 oxygen. If there's only 1, you're not going to see a subscript. These are somewhat similar to exponents, but they're down low and they represent the number of atoms. Okay, so next, molecular formulas. They represent how many atoms of each element are in a compound. So as we said before, 2 carbons, 8 hydrogens, and so on. Of water and glucose and so forth. Now, there are different types of formulas. One type is an ionic formula. It shows the simplest ratio of cations to anions that form the lattice. For example, if we mined a big chunk of salt, just sodium chloride salt, out of the ground, you could have millions upon millions of atoms and they're all bonded together. So it wouldn't do to write 20 million sodiums for every 20 million chloride atoms. So instead we keep the simplest ratio that works much better. Okay, sometimes in a chemical formula you're going to see sets of parentheses around groups of elements. And what that is, it's used around a polyatomic ion in a chemical formula. And usually when they're written, it's telling you that there's more than one of those ions. So here we have an SO4, so sulfate, with parentheses around it, and it says there's a 3 right outside. So what that means is there are 3 of these SO4s, 3 sulfates. And the reason that's done will be made obvious a little bit later. It has to do with balancing charges. So we have aluminum, 2 aluminums, 3 sulfates. We have 1 copper, 2 phosphates. We have 2 nitrates. And just so you don't get confused, the 4 here in the sulfate right here, this 4 means there are 4 oxygens, but there's only 1 sulfur per each polyatomic ion. Okay. Okay, monatomic ions. We'll start out simple here. Ions form from a single atom. And there's a pattern in the periodic table that if you can recognize and understand it, it can make things a lot easier for you. Okay, group 1 elements may lose 1 electron. This all has to do with octets and atoms wanting to have 8 electrons in their outer layer. So group 1 elements have 1 electron in their outer layer. If they lose that 1 electron, they will have a full octet underneath, generally. So if they lose 1 negative charge, 1 electron, they end up having an overall charge of +1 because they've lost a negative charge. Group 2, if they lose 2 electrons, their outer layer is now full, and they end up having a 2+ charge. Group 13, if they lose, well, to be honest here, the only one that really does this is aluminum. But okay, we'll say group 13. If it loses 3 electrons, it will have a 3+ charge. Now we can look at this the other way. Let's look at, the noble gases are group 18. So right next to them we have group 17. If they gain just 1 electron, their outer layer currently has 7 electrons. If they gain just 1, they'll have 8. So they gain 1 negative charge, 1 electron, so 1 minus. Group 16, 2 away from noble gases, gain 2 electrons, 2 negative. Group 15, gain 3 electrons, 3 negative. Now, these patterns don't apply for every single element in these groups, but it is a good trend to be aware of, and it can save you an awful lot of time when you're trying to figure out charges and balancing them. Transition metals, that big D block right in the middle of the periodic table, there's really no pattern to how these fill in. And we'll talk about those later too. Okay, so let's get into naming monatomic ions. Okay, you get a monatomic cation. Well, there's one atom. It's one element. It's simply called by the element's name. It could be calcium, potassium, sodium, whatever it may be. Monatomic anions, the negatively charged ion, ends with "ide." So fluorine gains an electron, you drop the end, and it becomes fluoride. Oxygen gains 2 electrons, you drop the ending and becomes oxide, and so on. You could have sulfide, iodide, phosphide, nitride. So if you're talking about just one element, the ending is going to be "ide." Okay, there's another system called the stock system. We will talk more about that a little bit later, but it's used when there's more than one possibility for an element. Transition metals are a great example of using this. We'll talk more about it later. Okay, binary ionic compounds. Compounds composed of 2 elements. And this is how you do these. This is really easy. You write the symbol for the ions with the cation first. The positively charged one always goes first. So aluminum positively charged, says so right here, 3 plus, because it lost 3 electrons. Oxygen, negatively charged, because it gained 2 electrons, says so right there, 2 minus. Okay, so the easy way to do these is cross over the charges. Let me show you how this works. You cross over the charges and write them as a subscript for the other ion. So aluminum was a 3 plus, right? So we're going to make that 3 plus be the subscript for the other element. Oxygen had a 2 minus, so that tells us that we need 2 aluminums to balance out the charges. So if we write 2 aluminums and 3 oxygens, our charges are balanced. And maybe I can write for you real quickly why this is. Okay, if I have 2 aluminums, each aluminum has a charge of 3. It's positive, right? So we'll put in another aluminum here, also with a charge of 3. So our total positive charges here is 6 plus. Okay. Now, if I want to balance that with the negative side, I have to have 6 there as well. Okay, so I've got an oxygen with a 2 negative. I got another oxygen. It said I needed 3 of them, 2 negative, and a third one, oxygen, 2 negative. So now all my negatives add up to 6 minus. So I got 6 plus, 6 minus. The whole thing's balanced and neutral. Everybody's happy. So that's why you can just take these charges and make them be the subscript for the other part of this compound. Okay, now let's see what you remember about naming these things. Remember the first, the cation, the first part of this compound, positively charged, just keeps its regular name. So we're just talking about aluminum. Al, well, this is hard to write with a mouse. And the second part was oxygen, but remember when it gains electrons, you drop the ending and you make it be ide, I-D-E. Aluminum oxide. Okay, so we've got a couple more examples here. We've got zinc and iodine, but this iodine has gained an electron, so its name is changed, right? So we have, why don't I do it this way? This will be a little bit easier than trying to write with a mouse. So we've got zinc iodide. Okay. And if we were to write out the formula for that, I guess I should have done that, huh? The formula for, why don't I do this? Why don't I get a little more room and I'll just put this over here. Okay, we need the formula, don't we? Okay, so we have the charge on zinc is 2, which tells us that we can take this and move it over to here. I can probably write this better this way. So we have zinc and we have iodide. Okay, the charge on zinc says it's 2 positive, so to balance that with this iodide, which is just one. Usually, if they just put a minus or a plus, it means it's just one. Okay, so I'm going to need 2 of these iodides to balance out with 1 of these zincs, because 1 zinc has a charge of 2 all by itself, and it takes 2 iodides to balance that with 2 negatives. So zinc iodide. Okay, same thing. Okay, let's look at these here. These charges are already balanced, aren't they? So we don't have to swap these. If they're equal, we really only need 1 of each. We need 1 zinc, which is 2, put it with 1 sulfur, or sulfide now, which is also a 2. So I can just write it this way. We got zinc and, oops, forgot my N, zinc sulfide. And I could write out the name real quick too. Whoops, technical difficulties. Zinc sulfide. And sometimes you'll see this spelled with a PH, S-U-L-P-H-I-D-E. Either one's just fine. Okay, so that's how we name those. Now, I said we talk about the stock system of nomenclature, and nomenclature is just a naming system for binary ionic compounds. Sometimes elements like, as I mentioned earlier, transition metals can form different cations. They can have different positive charges. So the stock system was developed to show their different charges by using Roman numerals. So we have copper here, and if we were to write it the way you just saw it a minute ago, we could have Cu plus, because it's positive 1, or copper could also be a Cu2 plus, and we need to know that. So when we write out the names of these, we put in Roman numerals. We'll put copper 1 or copper 2. We need to show that when we're writing out names of formulas, names of compounds. So copper can do this, tin can do this, many transition metals can do this. Pretty much every transition metal is going to have a positive charge on it. Okay, same method is used for binary ionic compounds. Chromium, again, transition metal, and fluorine combines to form chromium fluoride. So it's called, but we can't call it just chromium fluoride, because if we said that, we would never know. If I wrote just chromium fluoride without the Roman numeral in here, I could not go from this name back to the formula because I wouldn't know the charge on the chromium. So I have to say chromium 3 fluoride, so I know that the charge on the chromium is a positive 3. Then I would know that, okay, if I know that fluorine is a known because of what group it's in, I know what that is, and I can switch it back to this. So those Roman numerals can be pretty important. Okay, oxyanions and other polyatomic ions. Okay, when you get into polyatomic ions, we had endings before that ended with IDE. Okay, you get these polyatomic ions bond with oxygen in them. They can have different names. If there are more or less oxygens, as sulfate or sulfite, the endings would be ite for the lesser oxygens. Here we have 3, or ate for when we have more oxygens. Here we have 4. We could have nitrite, nitrate. We have 2 oxygens for an ite, 3 oxygens for an ate. And there really is no way no pattern to know that, okay, 3 of them is an ite, 4 of them is an ate. That doesn't work. You can see that here. There are tables that are filled with common ions, and you just need to know where to go to look them up. Now, sometimes there's the possibility of more than 2. We could have, okay, here we have a chlorite and a chlorate. And we have a perchlorate. If there's more than 2 possibilities, there's probably going to be 4. So you could have well, why don't I start with these? ClO2 is a chlorite. Funny looking C. O3 is chlorate. See, there's less and there's more. Now, if I have even more ClO4 would be perchlorate. But if I had less, which is also a possibility here, ClO, hypochlorite. Okay, so I think you kind of get that. And again, you can just look these up in the tables. Now let's make the switch to binary molecular compounds. Okay, there's two systems. The newer system is the stock system, as we talked about already. The older system uses prefixes. And first thing you're going to do when you find a compound is determine, do they have opposite charges, my different elements. If they do, you go with ionic and simply just balance the charges as we just did. But if they do not have opposite charges, you're going to need to use prefixes. And the general rules, you write the element with the lesser number of atoms. It goes first. And you drop the, okay, this is kind of a, if your element starts with a vowel, you are going to drop the vowel of the prefix. For example, well, oxygen, for example. Okay, you wouldn't go put monooxide. Well, here's an example that would be familiar to you. If you have this compound right here, carbon and oxygen put together is carbon monoxide, right? So you've been doing this, monoxide. It wouldn't be monooxide because you dropped this vowel right here. So it's monoxide. So your first element in your compound only will get a prefix if there's more than one. If, well, like we had right here, we had carbon monoxide. Carbon didn't get a prefix. But if I had, let's say I've got something like this, Si2O3. Okay, now there's two in the first one. Disilicon trioxide. Okay, probably clear as mud. Little practice, you'll have these down. Okay, our last slide of notes or explanation. An acid and salts. Acids refer to water-based solutions that, you know, they have unique properties. Binary acids, combined of hydrogen and usually something else. When these things break down, the hydrogen goes away, and what's left is going to bond with another charged particle, and it's going to form a salt. You know, you can probably read this without me reading it to you. Okay, what I've got left in this video, real quickly, because we're getting way longer than I want to be, is a couple of slides of practice. So what I'm going to do is I'm going to put these up here, and if you want to stop the video now before I uncover these, I don't think I'm going to go through them all because this video is getting so long. So go ahead and try and work through them, and I'm just going to uncover them. I've got another slide. I'll do the same thing. So here you go. Best of luck to you. Okay, got those, and I'm going to go to the next slide, and I'm going to do the same thing, and got some more. And because we're getting so long, I'm going to say that's it for this video. I hope this helps you out. Bye.